All right, let's look at the dynamic analysis of robotic manipulators. So we basically have two aspects, that is inverse dynamic analysis and the forward dynamic analysis. So in the inverse dynamic analysis, we have a robot and we are given a particular motion profiles of the joints, or it could be of the end effector, and we are supposed to find out the required torque to achieve such trajectories or to achieve such motions. So obviously motion is specified obviously in terms of time, so obviously the torque would also be, the torque profile would also be plotted with respect to time. So given the joint trajectories, we determine the forces required to achieve them. This is inverse dynamic analysis of robots. This is particularly useful in the control of robotic manipulators, as we want robot to basically follow a particular trajectory. So inverse dynamics actually helps us there. It actually calculates the torque for that trajectory. So this is the typical dynamic equation of motion that we see. The torque vector is equal to the inertia matrix, and the theta double dot is nothing but the vector of joint accelerations, which could be prismatic and revolute in general, and h is the vector of centrifugal and Coriolis accelerations, and gamma is the gravity vector. This also represented in the state space form like this: m theta double dot plus v theta comma theta dot plus g of theta dot. This is an alternate representation which actually tells us that gamma is actually a function of theta and h is a function of theta theta dot, and m is itself a function of configuration of the manipulator. Now this is how a typical joint trajectory is given. There are several ways in which joint trajectories can be specified. Trajectory generation is itself a chapter which we can actually discuss, but it's beyond the scope of this course now. But a typical trajectory that is given to the robotic manipulator is a cycloidal profile, that we want a robot to basically move from point 1 to point 2. So this is how it looks like. So your theta of any joint, theta could be theta 1, theta 2, theta 3 at any joint, is actually equal to the initial value of that joint, initial actually the configurational value, that is theta naught, plus theta final minus theta initial by time. This capital T is the total time that it needs to basically a robot needs to take from one position to another position, that is theta naught to theta T. What is the time the robot needs to actually reach this place in a specified time. And then we have small t is actually represents the actual time. So it's like if we have from 0 to 10 seconds, so it's like small t's will be as per steps, so it could be 0.01, 0.02, 0.03. So every time t updates the value, so t is could be here the computer time. Then we have t by 2 pi sine 2 pi by t, capital T into small t. So this is the known as the cycloidal trajectory. And if we know the joint trajectory, we should also know the joint velocity and the joint acceleration, which can be simply found by differentiating this expression with respect to time, so which will look like this. You can verify this later on. Then we can again find out the acceleration, which looks like something like this. Fine. So graphically, if we plot them, because capital T is constant, theta t, theta naught is constant, and pi is constant, so capital T is constant, so we just have small t as the variable. So theta obviously varies with respect to time, theta dot will vary with respect to time, theta double dot will vary with respect to time. So if we plot just these three and find out basically how they look like, so this is something trajectory over time plot. So if you look at the graph, we have the position profile that looks like something like this. This is the position profile, this one, which means a robot moves from 0 to 1. Let's say this is some normalized values, 0 to 1 in 0 to 1 time, normalized time. So it follows this type of trajectory. It could follow a linear trajectory like straight line like this, could be some piecewise kind of linearizations, or piecewise step inputs. So this is one of the trajectories that is selected. The good thing about it is that when it reaches to the top, the velocity profile is this one. This is the bell-shaped curve that we will get as the velocity profile. This is nothing but the previous equation that we have seen, this one, theta dot. If we plot this theta dot, we would get this bell-shaped curve. All right, and then theta double dot that we have seen in the previous slide, this one. So this would be this one. So the good thing about this trajectory is this cycloidal trajectory is that we have acceleration 0 at the beginning and 0 acceleration at the end, and we have 0 velocity at the beginning, 0 velocity at the end. This is something that is designed ideally for robots because we would like a robot to reach to that position without any overshoots. Obviously, for that we need acceleration to be minimum or 0 and velocity also to be 0 because those dynamic effects almost should die out at the end. Normally this doesn't really happen because of the other undesirable effects or other unmodeled effects in the robot. So there we do not really achieve the desired endpoints. We have to actually go for robot control that actually tries to make it achieve the desired profile. All right, so let's take some examples of inverse dynamic analysis on Matlab. So this is the Matlab environment. So we have a Matlab 2013 version here, and then we have the command window, we have the folder window here, we have workspace window, we have command history. Some of you may be already aware with Matlab. I already shared a link or a PPT of basic understandings or basic learning Matlab, so you can go through that. So this is how we write it in Matlab, just to visualize these torque profiles or do some inverse and forward dynamic analysis. So let's take first the one link example that we have already discussed in detail, the derivation. So let me just show you this pen. So this is how it looks like. So this is the command, this is the editor, or you can the script file that I have written. We have a clear command, CLCs, clear all. We write these commands initially at the beginning of each program so that the previous data that's in the workspace actually goes null and void. Then before I actually show it to you, if you look at this equation, tau is equal to ma squared theta d theta by 3 plus mg a cos theta by 2. This is nothing but the dynamic equation of motion of a one link robot or one link pendulum. So this is nothing but ma squared by 3 into theta double dot plus mg a cos theta by 2. So this is what we have already got in the one link analysis. You can refer to that analysis if you have any doubts. So this is how we write it in Matlab. So I have referred to torque as tau, tau is equal to m. So this is your multiplication, that is the asterisk sign, a, this is hat, 2 means ma square into, I have written double d theta, which means dd theta, that is theta double dot for me, divided by 3 because ma square by 3, and plus mga cos theta by 2. I hope this is clear. Now for this thing we require the definitions of m, a, dd theta, theta and g. So we call them as inputs. So we have just maybe specified it this way: input parameters in SI units. Mass is given as, let's say, 1 kgs. A is the length of the link, that is, let's say, 1 meters, and g is the acceleration due to gravity, which is 9.81 meter per second square. So this all has to be in SI unit for conformity with the torque again in SI units. These are, we can say, initial values. So we want a robot actually to move from theta is equal to 0 to theta is equal to pi by 2. So 0 to 90 degree we want it to move, and we want it to move in just 1 second. Capital T is the total time it should take, that is 1 second, again in SI units. And then we want a time profile which is in this form. This is how time actually increases from 0 to capital T in the form of steps. So it is nothing but a time vector actually. So this is the trajectory that we have just discussed. So theta is equal to theta I plus theta f minus theta I. Theta f means theta t, capital T, minus theta 0 by capital T into this. So this is what I have actually put up here in Matlab. But to be very careful about different ways we write the Matlab script, though it's not that difficult. So once we write theta, d theta and dd theta, we define them as per the definitions for the cycloidal trajectory. So obviously here we have small t, and in this case also we have small t here. In the theta double dot also we have small t here. So all these will vary with respect to this thing. So t, a small t will be a vector that will be created, and accordingly these theta, d theta and dd theta vectors will be created. Those will get embedded into this equation because we have dd theta here and theta. So though we don't require d theta in this case, it's not here, we don't have any Coriolis and centrifugal components. So all this would actually find out the torque. So we can then use something called as plotting functions. Plot small t comma tau. So we want to plot torque with respect to time. So this is nothing but just to make it a little evident in terms of the formatting. We can label x as time in torque and y as torque. So after we are complete with this, so we can actually run this program here by clicking on run, or we can also press F5. The moment I run it, so it's nothing but substitution of values, so we get torque like this. So this torque in Newton meters, this is time in seconds. So this is how the torque will vary. Initially the torque will be at least 5 Newton meters. This is actually because we have gravity, and obviously it has to withhold it at 0 angle, so obviously it needs some torque initially, and then the torque increases, the torque decreases, so obviously finally it has again some value, which is in this case obviously it has 0. So this is how the torque profile would, or the torque would vary for this configuration. Now you can see the maximum torque here is almost 8, and it goes to almost -3 here. So let's see if we want to make it do this thing faster. So we may say that let's achieve this all in just 0.5 seconds. So which means robot has to actually have more torque, has to actually exert more torque because it has to move faster. So let's see now. So what's happening is it's almost going to 16, so it's almost doubling. Initially it was 8, and then it's also again here going to almost -12 or -13. So that means the effort required, or the motor torque required, is now higher because we want to make it move very faster because of the simulation time being very low. And if we want to just make it slower, so we can keep a very high time and longer time duration, so obviously the amount of torque required will be lesser. So just 5 here and it's almost 0 here, which is quite evident. All right, so again we can also do some other things, like we can make it maybe again 1. If we decrease the steps to, let's say, 0.1 only, so we'll have less number of values, so it will look like something this. So this is quite evident. And if we just want to keep 0.01 as a better, this is almost 100 values. And if you want to decrease or maybe change this also, we can. So we can go from 0 to pi in just 1 second. So it will look like this. So we have almost 12 Newton meter of torque that is required, and we have almost -5 torque at the end because it has to withhold it with respect to gravity, so it will have some torque at the end also. Now we could also see a case where we don't have gravity, as we have already discussed that one link robot may not really act as a pendulum. It may be just it may act in the planar case where we don't have gravity actually. So in that case, if we simulate for the same 0 to pi, so we have something like this. It goes to almost 7 and it goes to -7. It's almost a symmetric profile similar to acceleration profile that we have seen, and we know this quite fact that it's 0 at the beginning, 0 at the end, because there is no gravity, so which is actually for which the robot has to withhold it at that position. So obviously this has to be 0, this will be 0 at the beginning, at the end also. Fine. So this is a one link example. We can also do this by putting all these parameters, initial values, trajectories in different files. That way I have done it here. So I have a trajectory file, so we can write a trajectory in a separate file. We can write input values in a separate file. So this is the input file, this is the initial file where I specify initial angles, and this is the dynamic model. Can be also written like this: capital M, capital B, capital G. And you can write this one link program like this. You invoke these commands: input, initial, and then you have simulation from time 0 to the maximum time, trajectory, dynamic model, and the equation of motion. So this is the general equation of motion that we write: capital M d d theta plus V plus G. We can write it this way also. So this also would work. You can just see it. This is the output. So this is an alternate way of doing it actually. Similarly, we can look at the other examples. We have two-link serial manipulator that we already discussed the equation of motion. So I have already put it here in the Matlab. So I have this two-link trajectory. So trajectory here will be for two links, so theta1 and theta2. So that becomes a vector. So theta now becomes a vector, theta1 and theta2. D theta becomes a vector, d theta1, d theta2. Similarly, acceleration becomes a vector. Similarly, we have inputs. Inputs would be small m, m1, m2, because we have two link manipulators. So we have two links with two masses, obviously different masses and different lengths, or we can have similar lengths. This is the definition of gravity. And then we have initial conditions also, because now we need to define for both the links. So we need to define the initial angles for both the links. That's defined here. And this is the dynamic model that we have already discussed. So these are those values of small m11, m12, m21. All those I have already put up here. This is the M matrix that I have written. This is the P components, and these are the G components. I have written all these things. And then we have the main program in which all these are actually called. So this is a calling function. You call these, maybe you can say it's not a function, it's a file that you are calling. In Matlab you can do those things: input, initial, and then trajectory, dynamic model, finally calculating tau as m theta double dot plus v plus g. So this is how it actually works. So these are the two profiles depicting torque 1 and torque 2 at the joints for tooling manipulators, two joints of tooling manipulators. Again, it's 0 at the beginning, 0 at the end, because we have taken gravity to be 0. And our inputs were that it should move from, our initials were that it should move from 0 to pi by 2. This is also theta 2 also should move from 0 to pi by 2. We can change this and then visualize what happens to the torque. Or we can change the gravity here. We can put gravity to be on rather than off, of 9.81, and then we can look at the changes in the torque. So initially without gravity we have 0 at the beginning, 0 at the end. Now if you look at this one, so we don't have 0 at the beginning, we don't have really 0 at the end. So this is the torque profile for this motion. So if you want, I can just change this to pi and let the other be at pi by 2 only. So I save this and then I go to the main program and then I run it. So we have a different profile now. Alright, so this is an example of a tooling manipulator. We have also an RP manipulator that we have discussed. So I have already put up its equations also. So these are the inputs of both the links. These are the initial conditions. Now in this case we have theta 1 and theta initial and theta final. We have initial value of the displacement, linear displacement, because it's a prismatic joint, and this is the dynamic model of this robot. So this also can be run. This is the value of the torque. This is the profile of torque and the force at link or joint number 2, because this is a revolute prismatic. So we will have torque at joint 1 and prismatic, it's the force at the prismatic joint. I can just show you one more example of doing it by a different program. So this is an example of an RP robot again, but it's a different configuration where the prismatic is placed in a different way. Could have this the way we have done it, but this is an animation and this is the torque plots for the same. And we can also look at the tooling example in this case, where I take these values. This is a program that has been designed to cater to all these in a more generic way. So this is a two-link manipulator. You can just see a 3D view. Two links. One link is supposed to move to some angle. The other is also supposed to move to some angle. You can see its view from. All right. These are the torque at two joints. Fine. So this is how basically we do inverse dynamic analysis, and we find out whether the model that we have developed is correct also, and also we find out the maximum torque required at the joints for different profiles, and we also use it for obviously design purposes. We know that for this trajectory what is the torque required, and accordingly we can select a motor for actually for that manipulator, for that robot. Similarly, we have forward dynamic analysis. In the forward dynamic analysis, we have given the input torque, joint torques. We determine the trajectory that the robot will follow. It's useful in simulation and analysis of robotic manipulators, because we would get enough forehand information about the robot, the robot motion, actually motion profile for a particular torque profile. So this was quite helpful in the design of robots, because we don't really design robots practically before we first simulate them. So this is how the equation of motion we have seen in the previous skill, but this is how it's now written for forward dynamic analysis. Theta double dot goes to the left, and then we have I inverse and tau minus h minus gamma. Now this is again alternatively written like this. So in this case, if you see that g theta v theta gamma theta dot tau and m again a function of theta is inverse. So we have the inversion of mass matrix or the inertia matrix, or we can also generalize inertia matrix generally in forward dynamic analysis. So this is quite significant. And what actually goes in is the torque tau and initial theta and theta dot, and then we also evaluate m theta, and inverse of that we get theta double dot. But then we have to do integration of this, which gives us theta dot, and then again integrating gives us theta. Those theta and theta double dot are actually substituted back to this point. We again calculate theta double dot. This is how we get the joint trajectories. So we have something called as free simulation, in which we just allow the robot to move freely under gravity. There is no external torque, and we find out the motion profile, and we see how much our simulation actually is good. And then we have force simulation, where we have torque profiles that we have obtained from sometimes from the inverse dynamic analysis of this robot, and then we use those as the input to the robot, and then try to see how it basically responds to the joint torque. But the initial configuration is generally specified, so joint velocity and position is obtained. So it's a big area of research, forward dynamic analysis, and we have something called as recursive forward dynamic analysis or recursive inverse dynamic analysis, because when the number of links in the robot increase and the complexity of the robot increases, so the computation time associated with these inertia matrix inverse of this inertia matrix is actually it increases. And then we use different techniques, different mathematical techniques actually to reduce them, or to find out similarities, to find out various properties associated with these inertia matrices, and we manipulate them to try to basically decrease the computational load, decrease the computational effort that is required, and try to basically improve upon the algorithms, what we call as forward dynamic algorithms. And then also some work is also goes towards inverse dynamic analysis, how we can basically analyze a robot and try to make its its model or its equation of motion simpler, or what are the simpler ways of doing it. So it's all about so many things that actually are taken as research topics. So that's it. Thank you very much.